So, hello everyone. Uh, my name is Ashish Chaudhary. I am one of the PMRF teaching assistants in this course, and today we will be discussing some of the problems related to the lectures that were conducted during the first week by Professor Ghosh. So, Uh, the name of this course, as you all know, is Geology and Soil Mechanics, and your instructor is Professor Priyank Ghosh, and myself, I am Ashish Chaudhary. I am a research scholar at IIT Kanpur in the Civil Engineering Department, and throughout this course, I will be discussing some of the problems after some problems related to whatever is being taught every week. So if you have any doubts, you can ask me anytime during the lecture, and after the lecture anytime you can email me any any doubt you have related to this course. You may contact me anytime, and I will try my best to help all of you. So let us start. So So the first thing that was uh, taught during this week, the first week, was how are soils formed, or how is soil formed. So as we all know, soils are formed from rocks. So how are soil formed? Soils are formed from rocks. So, but there is a condition. There is a case that rocks are also formed from soil, such as the case of sedimentary rocks, where soil deposits like soil gets deposited in layers, and we get sedimentary rocks. So, so one more topic which we have studied is the rock cycle. So in the rock cycle, we could see that how the various types of rocks are formed, and how soils are formed from those type of rocks, and again from the soils how those rocks are formed. So uh, so mainly rocks are of three types, as we know. First is the igneous rocks, second is the sedimentary rocks, and third is the metamorphic rocks. So these are the three types of rocks based on how they are formed, how the rocks are formed. So so the details of all of these were already discussed in the class, so I won't go into the details again. If you have any doubt regarding anything, you may ask me anytime. So after this we learned how soils are formed from this type of rocks. So the process, so soil is a very granular, like very microscopic kind of thing, right? So the soil particles are microscopic. So how are soils formed? So these rocks, actually what happened is that they undergo weathering. So weathering is the process through which soils are formed from the rocks. So weathering can be again of two main types. So one is your chemical weathering, another is your mechanical weathering. So in chemical weathering, what happens is the original soil structure, the structure of the uh, origin structure of the constituents that form the rocks, those get altered due to some chemical reactions, and the soils which are then which are then formed, they don't have the same what to say constituents as the parent rock, because there is some chemical reaction that takes place, due to which the properties are different in the rocks. And in mechanical weathering, what happens, there is just mechanical breaking of the rocks. So due to wind, due to like water, the rivers flowing over rocks, what happens, they disintegrate, the rocks disintegrate, and then from there we get the smaller particles which then form the soils. So this is the main gist of how rock soils are formed from rocks. Then Then we studied the types of rock, types of soils, soil types, soil types. So those were residual soils and transported soils. Residual and transported. So in residual, what happens is that the rock undergoes weathering and can then gets disintegrated into some particles, okay, smaller parts. So what happens, those soils are formed at the original location where this rock was situated. So that's why they are known as residual soils. And then the transported soils are formed, and what happens is that the particles, the rock particles, after disintegration or weathering, they are carried over through large distances by air, by wind, that is by wind, by river. So this way the transported soils are formed. And then we studied the types of transported soils, which were alluvial soils, which are formed by river, transported by river, okay. And then like this lacustrine deposits, lacustrine deposits which are formed with the help of lakes. The lakes, they transform, they deposit the big lakes, they'll deposit the particles, and these salts are formed. Then also we started marine deposits, okay. Then we studied aeolian deposits, and then aeolian means carried by air, okay, transported by wind, it is by wind. And then we studied glacial deposits. Glacial, it is the soil which are formed and transported by glaciers, okay. Then we looked into the three represented the soil as a three-phase system. So this is the basic, the very basic of soil, like soil mechanics, or the soil mechanics, where we first learn how to represent the soil mass. So this is a soil mass. This soil mass will contain the soil particles, and also, just a second, yeah, so this will contain certain particles, and also there will be voids, okay. So also in these voids there might be water, these voids might be filled with water, or there might not be anything, there might just be air present in them, okay. So this soil mass is represented as a three-phase system, where we have some solids, which are these granular soil granules which form the soil mass, so the soil solids. Then we have the water, water, and then we have the air, okay. So this is called the three-phase diagram, or representation of soil, okay. So we break down soil, we represent the soil in terms of the soil mass, in terms of the three constituent parts, that is the soil solids, the water, and air. Then we have a condition called fully saturated soil. So in fully saturated soil, what happens is that this is the total void space which is occupied, some amount is occupied by water and some amount is occupied by air. So if this whole void space, this whole void space is occupied by water, then it is known as fully saturated soil. So here you can see totally we have water. After this, there can be one more condition of dry soil, where what happens is that there is no water, the whole void space is occupied by air. So this is a dry soil condition, okay. So in a three-phase diagram, let me draw it here again. So this is the soil solids, this is water, and this is air. So we will have some weight of solids, we will have some weight of water. So do we have any weight of air? No, right? Air is weightless, so there won't be any weight. Then again, this side we can write like that, that the solids will occupy some volume. So those are volume of solids. Then we have the volume of water, and air, obviously it doesn't have any weight, but it occupies some volume, right? So it will have volume of air. So this total, the volume of air plus volume of water, represents the volume of voids. Okay. So using this concept, we will define some terms which are known as define some terms which are very important for the classification of the soil or defining a soil. So for example, if you want to like, if you just want to define the soil present in some location, so how will you communicate that this type of soil is present there? So you need some parameters, right? So we will look into those parameters. So next we have index properties. So what are index properties? These are there are some tests which are carried out to classify a soil. Those are known as classification tests. So in order to classify a type of soil, we need to do some tests. Those are known as classification tests. The numerical results obtained on the basis of such tests are termed as index properties. So from these tests, we will obtain some values, some numerical values. So those are known as index properties. Okay. Now what are the different index properties? The first one is the water content. So water content, what is the water content? Water content we generally represent by small w. So water content is your weight of water by weight of soil solids into 100%. Okay. So here comes a question like, is there any upper limit? Is there any upper limit of water content? No, right? Because water content can be anything. From 0, it can be anything, because the weight of water uh, can be anything, right? It can be like, say the weight of solid is 100 grams. Okay. So now the weight of water can be 100 grams, it can be 50 grams, it can be 1000 grams, it can be anything, right? So there is no upper limit of water content. Next we have the void ratio, which is represented by small e. So it is nothing but volume of voids divided by volume of solids. Okay. So similar to water content, there is no upper limit to this. Upper limit to void ratio, it can be 0, it can go up to anything. Okay. So next we have the porosity. Porosity is represented by small n and is defined as volume of voids by total volume into 100%. So does porosity have any upper limit? Does porosity have any upper limit? Yes, the upper limit is always 100%. So why it has suddenly porosity has an upper limit? Because see, this was a three-phase system. This is the total volume of voids. Okay, total volume of voids, and this is the total volume of the soil. Okay, so there is a upper limit because you cannot exceed 100%. So you cannot exceed 100%. Obviously, by looking at this phase diagram, you can easily say that you cannot exceed the total volume, right? There will be some, and obviously upper limit is always less than 100. Okay, it won't be like, it can be 99%, but or 99.99%, because there will be some soil solids. If there are no soil solids, then that is not a soil, right? So it will always be less than 100%. It cannot cross 100%, or it cannot be equal to 100%. If it is equal to 100%, there is no soil. Then we have the degree of saturation. The degree of saturation is represented by S. It is written as the volume of water by the volume of voids into 100%. Similar to this, what is the minimum value of saturation is 0% when this is also this portion is also occupied by air, it's 0%. And what is the maximum when this is also occupied by water, when this whole part is water, the total volume of what is water, it will be 0 to it will be 100%. So there is a upper lower limit and upper limit to saturation, degree of saturation. So here sometimes in we will see that the soil we call the soil completely saturated. It means that the saturation percent of saturation is 100%. Okay, 100% means that all the voids are occupied by water. So the soil mass, the soil volume is completely saturated. Next we have air content. So what is air content? Air content is nothing but volume of air by volume of the voids. So we can write this as 1 minus S, 1 minus the saturation. Okay. Then one more term related to air is percentage air voids. Percentage air voids is represented volume of air by total volume. Air content is representation against volume of voids, and here percentage air voids is a representation against the total volume. Okay. Then we have the bulk unit weight. So what is the normal basic definition of unit weight? Unit weight is weight per unit volume. Okay. So what is how do you define bulk unit weight? Bulk unit weight, or gamma B, is defined as the total weight to the total volume. Now what is the total weight? It is the weight of the soil solids plus weight of water if present by the weight of solids plus weight of volume of solids, sorry, volume of water plus volume of air. Okay, this is the definition of bulk unit weight. Then we studied what is dry unit weight. Dry unit weight means there is no water, it is completely dry. So gamma D will be weight of solids by total volume. Okay, so there is no water in this case because it's totally dry. It's just weight of water by total volume. Then we have saturated unit weight. Saturated unit means all the voids are occupied by water. So we have the saturated weight divided by the volume, total volume. Okay. Then one more term we have the submerged unit weight, or gamma sub. So what happens is that when a body is submerged in water, there is a buoyant force, right? A buoyant force acts, this is the weight acting downwards. A buoyant force acts against the weight, which is nothing but equal to the equal to gamma, means the unit weight of the liquid times the volume, submerged volume of the mass, right? So there is a buoyant force which acts. So due to which, what happens if a soil is completely submerged, its weight reduces due to the buoyancy. So it is represented as the submerged weight by the total volume. You can also write this as the saturated unit weight minus the unit weight of water. Okay. So after this, we have the unit weight of solids. Similar, solids is nothing but weight of the solids by volume of the solids, using the same definition. And then we have specific gravity of the soil solids. So what is specific gravity? It is nothing but the ratio of the weight of a given volume of solids to the weight of an equivalent volume of water at 4 degree. So how can we write this? We can write weight of the solids by the volume of solids into the unit weight of water. This will give the weight of an equivalent volume of water, right? So we can also write it as gamma S by gamma W. Okay. So always remember that GS always is between 2.65 and 2.80 for most of the solids. Okay. Now, what is grain size distribution curve? So, in order to classify a soil, the first thing which we need to do is to find the grain size distribution of that particular soil. So, what is grain size distribution curve? So, grain size distribution curve is nothing where we have the size of soil particles in the abscissa in log scale, and the ordinate we have the percent finer. Means, say we have a size here, say 10 mm, and say we have some value here, say 20, means 20% of the particles of that soil particles are finer than 10 mm. Okay. So this is the this is how we plot. So to determine the grain size distribution curve, what we need to do is we need to do sieve analysis. Okay, we need to do sieve analysis. So the sieve sizes vary from 80 millimeter to 75 microns. Okay, so this fraction, what we do is we take the soil sample, we oven dry the soil sample, and then arrange the sieves like this. See, we arrange the sieves are arranged like this. Okay, and here we have pan and put above a sieve shaker. Okay, so in the top jar it's 80 mm, top sieve it's 80 mm, and we go up to 75 microns. Okay, so we arrange the sieves, and the arrangement, there is a particular way of arrangement. First we put the 80 mm. Okay, then after 80 mm we put the 20 mm sieve, then we put the 10 mm sieve, and then 4.75. After 4.75 we can do 2 mm, 1 mm, 600 microns, 425 microns, 212 microns, 150 microns, and 75 microns. Okay, okay, so these are the sieve sizes. Okay, so we arrange all the sieves. Okay, so there is one more thing, that if the soil amount passing the 75 micron sieve is higher in quantity, we need to do the wet sieve analysis and hydrometer analysis. So first what we do is we do a dry sieve analysis. So in dry sieve analysis, whatever I showed you, we arrange the sieves like this. We put the soil above. Okay, we know the initial weight. We put the soil in the first jar, and when we start shaking this sieve shaker. So after a considerable time has passed, what we do is we take all the weights of all the soil retained in each of the sieve. Okay, we take the weight of the soil retained in each of the sieve. So what we do is we write a table, like here we have the sieve size, then we have the weight retained in each sieve, then we have the cumulative weight retained in each sieve, and then we write the percentage finer. Okay, so in this way we make a table. For a table we write down each sieve sizes here, 25 micron. So like this we make a table, you need to find out the percentage finer. Now while making this while taking the weights, if we see that the soil portion passing 75 micron is quite high. Okay, there is a large amount of soil passing through 75 micron. Then what we need to do is we need to do the wet sieve analysis. So in wet sieve analysis, what we do is we take the amount of soil that is passed through the 75 micron, 75 passing soil we take, and we wash with water. Okay, wash with water again. So we take the soil, so we take the soil, and then what we do is we put the soil above the 75 micron sieve and put water in it. So as we put water in it, what happens is that actually as the particle sizes are very small, there is a tendency that though they might stick to each other. So if the particles get they get stick to each other, what will happen is the apparent size will increase, so they won't pass through the seed. So what we do is we put water, we keep on washing the soil sample above the sieve. We keep pouring water and we keep on washing it. Okay, so what happens due to this, more amount of sieve will pass through the 75 micron sieve. Okay, more amount of this soil will pass through the 75 micron sieve. Okay, so so after this, what we do is the soil which is retained in the 75 micron sieve after this wet wash, after this washing it water is oven dried, and after oven drying it is again put into dry sieve analysis. Whatever we did like this, again it's passed through, like say for 80 mm, like 80 mm, 20 mm, again the same thing is done. And the fraction which is passed, and the fraction which is 75 passing fraction, what we do is we do the hydrometer analysis for this amount of fraction, the fraction which is passed through the 75 micron sheet. For this, what we do is we do the hydrometer analysis. Okay, so what is a hydrometer? A hydrometer looks like this, whatever is shown in the figure. This is the schematic representation of a hydrometer. This hydrometer is made up of glass. Okay, glass, and it is a very sensitive equipment. How does this work? This hydrometer works on the principle of Archimedes principle. Okay, so what we do is we take a jar like this, we take a glass jar, and the amount of soil that pass through the 75 micron, what we do is we take a particular, like say, set amount of water in this jar, and we pour this soil fraction here and we make a solution. Also, one more thing we put is that deflocculating agent. Okay, we put some agent, chemical in it, so that the particles don't stick to each other. Okay, and we make a solution here in this jar. Okay, so here we have a water type, a solution. This solution comprises of the soil which passed through the 75 micron sieve, some agent, some chemical agent, and water. Okay, and this water should be distilled water. Okay, distilled water. Okay, distilled water means that there should be no ionic property. That is, there should not be any minerals, because if there is any minerals, those minerals will uh, will like act as a flocculating agent. Those minerals will bind the soil particles with each other, and then the apparent size of those particles will increase. So we have to use distilled water. So what we do, we pour the distilled water, we pour the soil, we pour the distilled water in this jar, we pour some deflocculating agent or some chemical, and then we pour the 75 passing fraction in this, some set amount of fraction we put. Then we stir it up well and we make a solution. Now this hydrometer works on the basis of, I told you, it works on the Archimedes principle. Okay, it works on Archimedes principle. One second, just a second. Yeah, so it works on the basis of Archimedes principle. So How does it work? So what happens is that we make this solution, right? So after some time passes, some the soil particles will keep on settling down. Those particles will keep on settling down. So due to the settling of the particles, the density of the solution at the top will reduce. Okay, those particles are settling down, so density of the solution will keep on reducing. So as the density of the solution at the top of, like, in this portion of the cylinder keeps on reducing, what happens is that the buoyant force will keep on reducing. So as the buoyant force keeps on reducing, the hydrometer will keep on going down. Okay, the hydrometer will keep on moving down because the buoyant force is reducing. So using this principle, what we do is we keep on noting this hydrometer reading along against the time. So we have the hydrometer reading here, and there is time. So at 0 seconds, at regular intervals of time, we keep on noting this hydrometer reading. Okay, so we get many readings, and from those readings what we can do is we can find the percentage finer of a certain particle size which has settled down. Okay, so what we do is, so before doing this, what we need to do is we need to calibrate this to find out this effective height. Okay, so this was already discussed in the class, so I won't go in detail. So we need to calibrate this height, effective height, and to find the corrected reading of the hydrometer. Okay, so one more thing is that there are some changes, main changes which happen in the corrections which need to be done in this hydrometer reading. Okay, so the main three corrections are your correction due to the meniscus. So what is the meniscus correction? So what happens is that this is the water in the jar, right? This is turbid, and your hydrometer is poured inside. Hydrometer is inside, so you need to take this reading. So water, water will form some meniscus here, like some, that water will form some meniscus. So what we do is that we always take the upper level. Okay, upper level. So as we take the upper level, we need to incorporate some meniscus correction. So your meniscus correction is always positive. Then we have the correction due to temperature. So if the hydrometer is always calibrated at 27 degrees Celsius, so if the temperature is higher, then the correction is added, and if the temperature is lower, then the correction is negative. And one more is the dispersing agent. So I told you that we pour some deflocculating agent in the solution, due to which, so that the soil particles do not coagulate. Okay, do not coagulate. So due to that chemical, there will be some change in the density of that solution, so that also we need to correct. Okay, so the dispersing agent correction is always negative. So then we get the corrected hydrometer reading, which is our RH, which the reading that you took from here. You saw the hydrometer level and you took the reading. This plus the meniscus correction, plus minus your temperature correction, and always minus your dispersing agent correction. So then you get this corrected hydrometer reading. Okay, so now from the calibration chart, you will get this corrected reading versus the effective height. Corrected reading versus the effective height relation you will get from the calibration chart. From this corrected reading, you determine the effective height, and from that effective height, you can determine the size of the particle. So there was a formula which was given. This formula is actually based on Stokes law. So using the relation which was taught to you in the class, that relation, you can determine the size of the particle. So in this size of the particle is a function of time, time and this effective height. Okay, from there you can determine the size of particle, and after this, after determining this, from this size you can determine the percentage final. Okay, percentage finals, so that you can complete your this table, so that you can complete this table after 75 micron. Also you might have say 1 micron, zero 0.5 micron, you can complete this graph. Okay, after you get everything, you can just plot your grain size distribution curve, and from there we can classify the soil. So some important parameters of this grain size distribution curve is, one is your D10. So D10 is called the effective size. Okay, D, this is D10 is nothing but the size corresponding to 10% finer. Okay, so you have the grain size distribution chart. Here you have the percentage finer and you have the sizes here. So corresponding to 10%, you will get some size. This is nothing but your effective size. Okay, then you have the coefficient of uniformity, which is nothing but the D10 by D60, means so here will be some 60% number. So you have some curve like this. So whatever bit, so from there you will get some value here. From 60% you will get some size, that is your D60 size. Then D60 by D10 will give you the coefficient of uniformity. So if the coefficient of uniformity is greater than 4, that means your soil is uniformly graded for gravels, and for sand it should always be greater than 6. Okay, and one more term is the this CC term. Okay, this CC, if this CC coefficient of curvature lies between 1 and 3, this means that your soil is well graded. So you need to satisfy this both these conditions to call your soils well graded. Okay, so what does well graded soil means? Well graded soil means that a good amount of sizes, like good portion of each sizes is present in our soil mass. So this will be our well graded soil. Okay. Okay, then we studied the consistency of clays. So what is consistency of clay? It is nothing but the degree of firmness, means how firm, when you touch a soil, how firm is the soil. Okay, so in this, there is one thing called Atterberg limits. So what are Atterberg limits? So there are four kinds of states. Okay, states a soil can have. One is the liquid state, one is the plastic state, one is the semi-solid state, another is the solid state. So if we look into this graph, this is called the Atterberg limit graph. So what is, so in the x-axis we have the water content, and in the ordinate we have the volume. So as the water in the soil volume increases, the soil will be more liquidy. Okay, the soil will be more liquidy. So the soil will attain this state. So this is nothing, the state, so the water content after which the soil is negligible shear strength, means it doesn't have any strength and it just flows. Okay, it doesn't have any firmness, it just flows. This is called the liquid limit. Okay, then if we keep on reducing the water content, our volume will also reduce. Okay, so this is the, then we get the plastic limit. Between the plastic limit and the liquid limit, the soil is in the plastic state. Plastic state means that it can be molded, like a potter's clay, right? The potters actually operate in this region. They make various like say diyas and all, like diyas or some utensils out of clay. So for that, the soil needs to be in the plastic state. Okay, then if we further reduce the water content, we will enter the semi-solid state. Okay, semi-solid state. So this is the liquid limit, then this is the plastic limit, and below this there is another limit which is called the shrinkage limit. So very important property of this shrinkage limit is that up to the shrinkage limit, the soil is completely saturated. Okay, at the shrinkage limit, the soil is completely saturated. Now from the shrinkage limit, if we keep on reducing the water more, the volume remains constant, okay, but the soil is no more saturated, it will keep on drying, okay. So these are the main three water contents, which is the liquid limit, plastic limit, and the shrinkage limit, okay. So how to determine this liquid limit and plastic limit? Say you have a soil sample, how to determine this liquid limit and plastic limit? So what we do is that to determine liquid limit, we use this apparatus called Casagrande's apparatus, okay. This is the Casagrande's apparatus, okay. So this is the Casagrande's apparatus. So here what we do is that we take a certain amount of soil. The soil should be passing through 425 micron. You just please check this number. As far as I remember, this is 425 micron. So a certain amount of soil passing through 425 micron is taken, and then what we do is that we put some water in it. We push some water in it, and we make a paste. We make a paste, and we fill this apparatus here. Fill this cup. Okay. After we fill this cup, we use a tool. A tool is nothing but how should I explain? It's a tool made up of some metal, okay. So this tool is actually of this kind of something like this, looks like this, okay, very small, like the size of your pen, okay. Pen, but width is very high, okay. This width is quite high, like say about 4 centimeters, 3 to 4 centimeters, and length of a pen. So you have this apparatus. So using this apparatus, what you do is that you make one groove in the soil paste that you made. You make one groove, okay. After you make that groove, what you do is you keep on turning turning this machine. So if there is one handle, if you turn this handle, what happens is that this cup will keep on hitting this plate. So there are some sort, so keep on hitting this base, okay, like tuck tuck, it will keep on hitting this base. You keep on turning, and this cup will keep on hitting this base, and if from here you can see the number of times it has hit the base. It is the number of blows that you have given, okay. So then what you have, as you are giving this number of blows and it is hitting this base, the soil will keep on coming closer, okay. So what happens is that around after a considerable see, this specification is given in the IS code. You can look into the IS code or any standard book. So after this particular amount of soil has come close to each other, what we do is you note down the number of blows, okay. So here we have the water content, you have the number of blows. You would note down the number of blows. Then what you do is you take out this soil from the cup. After taking out, you find you take some representative amount of soil and you put into the oven to find out the water content. So you will get some water content and some number of blues. So again what you do is, again you make one paste with higher water content, and again you write the number of blues. So like this you will be getting a series of water content and number of blues, okay. So then what we do is we plot a graph. So here we have the number of flows in log scale, and in the ordinate we have the water content. So what will happen? It is very intuitive, right? So it is very much intuitive that if the water content is high, obviously the number of blows required will be less, because the soil mass will be more flowy, right? So if the water content is high, the number of blows required will be less. So we will get the points here, okay, like this, some points we will get, and then if we join these points we will get a straight line, okay. A straight line you will get. Now corresponding to 25 blows, the water content that we get, this is the liquid limit, okay. This is how we determine the liquid limit. All these details are generally will be discussed in your respective colleges in your geotechnical laboratory. So there you can like understand it more better. And many videos are also available in YouTube. So you can see those videos to better understand how this experimentally how do we determine this liquid limit. And one more thing is the plastic limit. So how do we determine this plastic limit? So for plastic limit, what we do is uh, we take a certain amount of soil. What we do is we roll it. Okay, so we roll using we keep it above a glass plate and we keep on rolling it so that its diameter is about 3 mm. So after reaching 3 mm, if it starts to crumble, means if the soil thread starts to break, that means that the water content of that part is your that amount of the water content at that point is your plastic limit. So what we do is take some amount of soil, we make some paste, then we keep on rolling it so that the thickness is uniform and it is 3 mm. The point when you have reached 3 mm thickness and it breaks there, it starts to crumble, mean it's just starts to disintegrate. That soil thread starts to disintegrate. That point is your plastic limit. Okay, so what you do is you measure the water content of those crumbled soil, that will give you the plastic limit. Okay. So next we have the plasticity index. Okay, so what is the plasticity index? Yeah, one more thing. This graph which you get, this is called the flow curve. Okay, this is called the flow curve. Now, what is plasticity index? Plasticity index is nothing but liquid limit minus plastic limit. Okay, so if the plasticity index is high, if the plasticity index is high, means the soil is highly plastic, means it is very much moldable, it's very plastic. And if it's low value means it's very less low plastic. And if it's zero, if the plasticity index is zero, that means it's non-plastic. Non-plastic means that it cannot be molded like a potter's clay. Potter's clay, it cannot be molded like that. So if it's zero, then it's non-plastic. If it's less than 7, it's generally called as low plastic. If it's between 7 and 17, it's called medium plastic. And if it's greater than 17, it's called highly plastic. Okay. Now one more term which we need to study is relative density. So what is relative density? Relative density is only valid for cohesionless soils, means granular soils like sand, right? Not like clay. Clay is sticky, right? Not like clay. This is valid mostly for cohesionless soil. Like this is used mainly to define the amount of degree of packing in a cohesionless soil. That is a degree of packing in granular soils, kind of for example in kind of sands. Okay, so what is the relative density? The relative density is defined as this: E max minus E natural by E max minus E mean into 100%. Means at the top you have the void ratio of the soil in the loosest state. Loosest state means maximum void ratio, so E max minus the void ratio in the natural, means whatever like say you went to some place and there is some sand. Okay, so you need to determine the relative density. So the in situ void ratio of that soil is the your E natural, and then in the denominator we have E max minus the void ratio in the densest state, which is your E mean. So there is a apparatus available, relative density test is there, proper test we can do in the lab to find out our E max and E mean. So using that we determine the relative density. So higher the relative density means that the soil is more densely packed. Okay. So if the relative density is more than 80%, we call it very dense. If it's 65 to 85%, it's dense. if it's 35, if it's between 35 to 65, it's medium. If it's between 15 to 35, it's loose, and if it's less than 15, it's very loose. Okay, so after this we will be looking into some of the problems. So we'll be discussing some sample problems. So if you have any doubt, you may ask me anytime. Okay, so the first problem, we see that a soil sampler of volume 1000 cc is used to collect soil samples. It was found that the sampler contained 2 kg of soil with dry unit of 1800 kg per meter cube. Okay, so if 400 gram of water is mixed to the soil, then we need to find out what will be the resulting water content of the soil. So let us write in what we have. We have the dry unit weight. So we have the dry unit weight as 1800 kg per meter cube. Okay. Then from this we can find out the weight of the solids. So what will be the weight of the solids? The weight of solids is nothing but the dry unit weight multiplied by the volume. Okay. So what is our volume? 1800 is a dry unit weight and our volume is 1000 cc, means 1000 into 10 to the power minus 6 meter cube. Okay, so we get 1.8 kg as the weight of the soil solids. Okay, but it was found that the sampler contained 2 kg of soil, means in this sampler there is some soil, the volume is 1000 cc, and in this sampler the total weight is 2 kgs. Now just now we determined that out of this 2 kg the soil solids occupy 1.8 kg. Okay, the soil solids occupy 1.8 kg. So if the soil solids occupy 1.8 kg, you can determine the weight of water. Initial weight of water, what is it? 2 minus 1.8 is equal to 0.2 kg. Okay, now let us look into this part. So what is written? If 400 gram of water is mixed to the soil, then what will be the water content of the sample? So what will be a new weight of water? It will be nothing but 0.2 plus 400 gram, 0.4 equal to 0.6. Okay, 0.6 gram. Okay, now as per the definition, what is the water content? What is the water content? It's the weight of water by weight of solids into 100%. So your weight of water, new weight of water is 0.6 divided by the weight of solids. Weight of solids is 1.8 into 100%. This will give you the water content. So let me just calculate it. 0.6 divided by 1.8 into 100 is nothing but 33.33%. So you get 33.33%. 33.33% is the new water content of the soil. Okay, so let us look into the next question. So in the next question we have an overnight soil has a specific gravity of 1.5 gram per cc. So from here we can write that overnight soil means there is no water, there is just soil. Okay, overnight soil has specific gravity of 1.5 gram per cc, means your dry unit, okay, is gram per cc. So let us write it like this, is 1.5 gram per cc. If the bulk density of the soil in natural state is 2 gram per cc, then what is the water content of the soil in its natural state? Okay, we need to find the water content of the soil in the natural state. Now, so we have the specific mass specific gravity, that of the soil is dry, right? So gamma d by gamma w. Okay, so this is given as 1.5 by 1. So you know in gram per cc what is the density of water? That is nothing but 1. So we'll have 1.5 as the mass specific gravity of this soil. Then what is the bulk density? The bulk density gamma T is given as 2 gram per cc. Okay. We need to find out the water content of the soil in its natural state. So there is one very important relation, that is gamma D is equal to gamma T, gamma total means the bulk unit weight divided by 1 plus water content. Okay. So this is a very important relation which is also very helpful in the Proctor test, which you will be learning in your geotechnical laboratory. This is a very important test uh, using which we can find out the dry unit weight of the soil when you know the total unit weight and the water content. Okay, so using this relation, if we put our values, we have 1.5 as the dry unit weight, and here we have 2 as the total unit weight, 1 plus W. Okay, so if you solve this, you will find W as 33.33%. Okay. Now let us go to the next question. Okay, so consider the phase diagram shown in the figure and determine the water content, the void ratio, the porosity and the saturated unit weight. Given the specific gravity of soil solids, means our GS is 2.6. Okay, so let us first see the water content. So what is the water content? The relation of water content is nothing but weight of water by weight of solids into 100%. So if we look into this figure, so what is the weight of water? It's 20. What is the weight of solids? It's 100 to 100%. This is how water content is 20%. Okay. Now second, we need to find out the void ratio. So this is one very important relation between void ratio and your saturation, is that E is equal to water content into G by saturation, degree of saturation. Okay, so what is the water content? We just determined that the water content is 20%, 0.2. Also we have the uh, specific gravity, which is 2.6. Okay, 2.6, and then the saturation. So if we look into this phase diagram, you can see that all of the voids, it's covered, it's occupied by water. There is no void, there are no air in, there is no air in it, right? There is just soil solid and water, there is no air. So 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 we can say that the soil is completely saturated because there is no air in it, so all the voids are occupied by the water molecules, correct? So what we do is, so that means that the saturation is 1, that is the soil is fully saturated. Okay, 100% saturation, so we put 1 here, so we get the void ratio as 0.52. Okay, next we have the porosity N. So we know the relation between porosity and your void ratio is nothing but E by 1 plus C. Just plug in the values of E here and you will get the porosity as 0.34. Okay, then next we need to determine the saturated density. Okay, we need to determine the saturated unit weight of the soil. So what is the formula for a total unit weight, or the relation of the total unit weight with the saturation, void ratio and the specific gravity? Is nothing but G plus SE by 1 plus E into gamma W. Okay, so for as the soil is saturated, completely saturated, your S is equal to 1. Okay, where S is equal to 1, so this T becomes the saturated unit weight, is equal to G plus E by 1 plus E into gamma W. Okay, so here you just put the value. So what is the value of G? It's 2.6. Then E was 0.52. 1 plus 0.52 into gamma W, let us say it is 10. So we will get this as 0.2153 kilonewton per meter. Okay, so this was very simple. So everything was, the phase diagram was given to us. This phase diagram was given to us. We just had to determine these parameters with the help of this phase diagram. So the first thing after we looked into the phase diagram, we saw that there is no air. There is no air. There is only water and soil solid. So the first thing that should come to our mind is that the soil is completely saturated. So our saturation is 100%. Okay, the percentage of saturation is 100%. It is as equal to 1. Okay, so this is one very important thing, important fact that we used to determine the value of our void ratio, then subsequently determine the saturated unit weight of that soil. So now let us look into the next question. So this question, you can see soil sample A and B have void ratio of 0.5 and 0.7 respectively. Okay, there are two soil samples A and B. One soil sample A has 0.5 void ratio and the soil sample B has 0.7 void ratio. If 1.5 meter cube of soil sample A and 1.7 meter cube of soil sample B are mixed, means both of these soils, some 1.5 meter cube of soil sample A and 1.7 meter cube of soil sample B are mixed together to form is another sample. We are calling it sample C. Okay, the volume of this sample is 3.2 meter. Then we need to determine what is the porosity of this sample C. Okay, so we have the void ratios of A and B. We mixed both of them. We need to find out the porosity of this soil sample C. So let us see how to find it. So for soil A, we have our E1. This is the porosity. We are writing it as 0.5. We have its volume as 1.5 meter cube. Okay, for soil B, we have its void ratio at 0.7 and the volume as 1.7 meter cube. And for for soil C, we need to find out the void ratio. We know the volume, it's 3.2 meter cube, right? So if we mix these two soils, the only thing that is going to remain constant is the volume of soil solids. Means the soil solids from A will soil solids of A and the soil solids of B. This both of these things are going to be always constant. Okay, so we will be using this particular fact to determine the porosity or the void ratio of C. So let us see. So for the soil sample A, how can we, the volume of soil solids of A means 1. We are considering it, calling it 1. We are calling it 2. Calling it 3. Okay, so VS1 we can write it as total volume of A by 1 plus E1. Okay, we can use this relation. So using this relation, we can find out 1.5. We know the volume of 1.5. 1 plus 0.5 is nothing but 1 meter cube. Okay, so we got the volume of soil solids of A. Similarly, the volume of soil solids of soil B can be find out 1.7 by 1 plus 0.7, nothing but again 1 meter. Okay, now Yeah, 1 meter cube. So what is the total volume of solids in sample C now? Means what is our Vs3, which is nothing but Vs1 plus Vs2, that is our 2 meter cube, correct? The soil solids are always going to remain same. So in soil, so we are taking soil sample A, sample B, we are mixing them. So what will be the volume of soil solids in sample C, soil C? It will nothing but 1 plus 1, 2 meter cube. Okay. Now we know that the volume of the soil, total volume of the soil C is 3.2. So out of this 3.2, you just calculated that the soil solids occupy 2 meter cube. Okay, so what will be the volume of voids? Nothing but 3.2 minus 2 equal to 1.2 meter cube. Okay, we got this. Now we have all the data that was required. So finally we can calculate the porosity. The porosity of sample 3 is nothing but volume of voids. Okay, volume of voids by total volume of our sample 3, sample C. This 1.2 by 3.2 equal to 0.375. Okay, so the main catch in this problem was that the soil solids will always get added up. Okay, because the soil solids always remain constant. So what we did was we find out the soil solids in sample A, we find out the soil solids in we found out the soil solids in sample B, we added them up, and that number will be the soil solids in sample C. So you use that to determine the porosity of sample C. Okay, yeah. So let us look into our next problem. So a sampler with a volume of 60 cc, 60 centimeter cube, is filled with a saturated soil sample. Okay, a sampler with a volume of 60 cc, it filled with a saturated soil sample. The specific gravity of soil solid is 2.65. Okay, it's given to us the specific gravity. When the oven dried soil is poured into a graduated cylinder filled with water, so there is a cylinder, graduated cylinder, like a cylinder, its there is graduated means some markings are there. So when we put the oven dried soil sample in that water, what we see that 40 cc of water comes out of that. It displaces means 40 cc of water comes out of the graduated cylinder. Say that cylinder is completely filled up, and if we are pouring some soil solids in that water, so what happens is that 40 cc of water comes out of, obviously it will replace the amount of water, right? It displaces the amount of water, right? So 40 cc of water will come. So this is the data given to us. We need to find out what is the natural moisture content and dry unit weight of the soil. Okay, so by looking at this question, we can see understand that when dry soil is poured, that means dry soil means only soil solids are there. Okay, soil solids are there, that when we are pouring this dry soil putting this dry soil into this cylinder, it displaces 40 cc of water. What does it mean? It means that the volume of this dry soil is 40 cc, because it's going, obviously it's going to displace the same amount, the same volume of water as the amount of volume it occupies, right? So it displaces 40 cc of water, means that its own volume is 40 cc. Okay, so from here we get the volume of solids is 40 centimeter cube. Okay, also it's given to us that the volume of the sampler is 60 cc, 60 centimeter. Okay, 60 centimeter cube. So from here we can easily find out our volume of voids. It's nothing but the total volume minus volume of solids, which is nothing but 20 centimeter cube. Okay, now we have some information, so using this information we can easily find out the void ratio. What is the void ratio? Volume of voids by volume of solids. Okay, volume of voids by volume of solids, which is 20 by 40, is nothing but 0.5. Okay, we got the void ratio. Now if we see the soil is completely saturated, our sampler, okay, is it is saturated sample, means in the sampler the soil is completely saturated. Okay, that means S is equal to 1, saturation is 1. So you have this value with the saturation, we have the void ratio. Okay, and one more thing which we have is the acid gravity of soil tillage, which is nothing but 2.65. Okay, now using the relation Se is equal to water content into Gs, we can determine the water content. What is the water content? It will be Se by Gs. It is 1 into 0.5 by 2.65, which will be nothing but 18.86%. Okay, we got the water content. Now, previously also we had used one relation which was our bulk unit weight, sorry, our dry unit weight is equal to the bulk unit weight divided by 1 plus water content, right? We have this relation. Okay, also our gamma t, this can be represented by another relation which is this, correct? As our soil is completely saturated, our S is equal to 1, so it will be G plus E by 1 plus E is nothing but, let us put the values, 2.65 plus 0.5 by 1 plus 0.5, which is nothing but 2.1 gram per cc. Okay, so we know this gamma t now. So we know this gamma t, we know this water content, just we can easily determine this dry unit weight. So what will be your dry unit weight? Thing was 2.1, 1 plus 0.1886, because our water content was 18.86%, 86. So we get 1.76 gram per cc as our dry unit. Okay, so let us again see how did we solve this. So a sampler with a volume of 60 cc is filled with saturated soil sample. Okay, this is our soil sample. Also it is known specific gravity of the soil solids was known to us. Okay, then uh, then one more fact about this soil, we know that when the soil is oven dried, the same soil is oven dried and poured into a graduated cylinder, it displaces 40 cc of water. That means the volume of soil solids, we knew from this the volume of soil solids was 40 cc. From this we could find out the volume of voids. After, as we know the volume of voids, we could easily find out the volume of the void ratio. Then using the void ratio we found out the water content. Now after this we got the total unit weight, and from this total unit weight finally we found out the dry unit weight. Okay, so now let us look into the next question. A compacted cylinder specimen of 50 millimeter diameter and 100 millimeter long is to be prepared from dry soil. Okay, we need to prepare a specimen and the dimensions of our specimen are already given, specified to us, that is 50 mm diameter and 100 mm. Okay, we need to prepare this from dry soil. If the specimen is required to have a water content of 15% and the percentage of air voids is 20%. Okay, so we need to prepare this sample. Okay, so the dimensions of the cylinder, compacted cylinder is given to us. Okay, dimension of the sampler is given to us, and two more criteria are mentioned. Those are, the specimen is required to have a water content of 15%. Okay, the specimen should have the water content of 15% and the percentage airport should be 20%. Okay, so these are the things that we know. Now to prepare the sample, one more thing we should determine is the weight of the soil and the water. Okay, so that we can make this specimen, right? So we have to mention criterias, and using those criteria, we will get, using those values, we will calculate the weight of the soil which we need to take and the amount of water that we need to take, so that we can make the soil sample. Okay. Also, the specific gravity of this soil is given. So let us see how to solve this. So the dimensions of this cylinder are given, which is nothing but 50 mm diameter, 100 mm length. Okay. So using this, we can find out the volume of the soil sample. Okay. The volume of the soil sample is equal to volume of the cylinder. Okay. Nothing but the volume of the cylinder, which is nothing but pi by 4 into d square h. So our d is 50 mm, h is 100 mm, which if we put this data, we'll get our volume is 196.35 cc. Okay. Now next, what is water content? Water content is nothing but weight of water by weight of soil. Okay. So weight of water we can write as volume of water into the specific weight of water, the unit weight of water, and the weight of soil solid we can write as the volume of soil solids into the unit weight of soil solids. We can write this again. From this we can write, so gamma s by gamma w is nothing but g. It is a specific gravity. Okay, so you can write vw by vs into g. Okay, you can write this very well, because gamma s by gamma w is g. From this we can easily get this, correct? So now let us, so now we know the water content. So what is the water content? Water content is 15%. So 0.15 is equal to volume of water by s into g. Okay. From here we can write volume of water is equal to 0.15 vs into g. Okay. Now what is our g? G is nothing but 2.69, which is given to us. So we have Vw is equal to 0.4 into Vs. So we got this relation from here. Okay. From water content, we got this relation between volume of water and volume of solids. Okay. Now what is percentage air voids? Percentage air voids is nothing but volume of air by total volume. So it is given to us that the percentage air voids should be 20%, right? So it's equal to 0.2, correct? Implies Va is equal to 0.2 V, correct? Right? Now what is a total volume? Total volume is nothing but volume of solids plus volume of water plus volume of air. Okay, right? So this volume of solids we keep it same. Now volume of water we represented in terms of volume of solids, which is nothing but 0.4 Vs. So we write it as 0.4 Vs plus we have the, again we have this relation also, Va, volume of air voids, is nothing but 0.2 V. Okay, so from this we can write 0.8 V is equal to 1.4 Vs, correct? Therefore Vs is equal to 0.8 V by 1.4. Okay, so 0.8 into, now what is the total volume? The total volume is this much, 196.35. So we write Put it to 196.35 divided by 1.4. That is, our volume of soil solids is 112.20 cc. Okay. So our task was to determine the weight of soil. Okay. First task is to find out the weight of soil. Okay. So we got the volume of soil solids. So now easily using this we can find out the weight of soil. It's nothing but G into ES into gamma W. Okay. Because G, what is G? G is nothing but weight of solids. What is G? G is nothing but weight of solids by Vs into gamma W. Okay, this is G. So using this, you can find out the weight of solids. This 2.69, 2.1, 2.2 into 1 will be 301.82 gram. Okay, so we just got the weight of, we just solved the first part, that is the weight of the soil we determined. Okay, next we need to determine the weight of the water. Okay, how to determine that? So our weight of water is nothing but the water content into the weight of solids, right? So what is our weight of solids? It's 301.82 gram. Okay, so 301.82. And what is our water content? It's 15%, so 1.5. We get 45.27 gram. So we found out both the things. It is the weight of soil solids that is required and the weight of water that is needed. Okay, so let us see what all that we did. So first, the specimen dia and the length of the specimen was given to us. So from there we determined the total volume, that is required. Okay, total volume was 196.35 cc. Okay, then the water content was known to us. So using the water content, we found out a relation between the volume of water and the volume of soil solids. Okay, next, our percentage air words was also specified to us, which was 20%. So from there, using the relation between air volume of water and volume of soil solids and total volume of air words, we found out the volume of soil solids. So our total volume we can write as a sum of the volume of soil solids plus volume of water plus volume of air. So we replace the volume of water with the relation which we determined back, and also the volume of air with the relation determined here. So using those two relations, we just determine the just rearrange the equation and determine the volume of soil solids. Now, if we know the volume of soil solids, then we can easily determine the weight of the soil solids, because we know the specific gravity and the gamma, like the unit weight of water, right? So specific gravity times the unit weight of water, specific gravity of soil solids times the unit weight of water will give you the unit weight of unit weight or density of the soil solids. Okay, so these two multiplied, this will give you the unit weight of soil solids. Unit weight of soil solids multiplied by the volume of soil solids will give you the mass, weight. We got the weight of the soil solids, and then also the water content is known to us. So just what we did was we multiplied the water content with the unit weight of soil solids to get the amount of water that is needed. Okay, so it's very simple. So now let us look into the next problem. So this problem is like an extension of the problem of the, like we did one problem, right, where two soil samples, so sample A and sample B, were mixed together to get a third sample, sample C, and we were asked to find some parameters of that sample, right? Some values like the void ratio or the porosity of that third sample. So that was a very idealized kind of problem, right? So now in practical field, a problem can be there where you need to build an embankment. Okay, embankment, you need to build a soil embankment like this. Okay, it's very long, right? We need to build an embankment. So how will you build an embankment? We need to carry some soil from a different location and then compact it and put it so that you can build that embankment, right? So these type of problems, we will be looking into this type of problem next. So soil from some different location need to be brought to some different location, and we know the density, uh, density, our density which should be there in this embankment. So we need to find out the how much amount of, like, how much should be carried from that place, different place. So let us look into the question. So we have an embankment is to be constructed. The soil is to be compacted at a maximum dry density of 18 kilonewton per meter cube at OMC equal to 15%. Means this uh, soil like the embankment soil has to be compacted, means like we need to compact it and make it densified so that the dry density it's 18 kilonewton per meter cube. The dry density of the embankment soil should be 18 kilonewton per meter cube at an optimum moisture content of 15%. Means the water content should be at that dry density should be 15%. So this maximum dry density and optimum moisture content, these things you will it will be taught to you in the compaction chapter very thoroughly, where you will learn about the Proctor test and how to draw the OMC versus dry density curve and all those things, like the water content in the dry density curve, and from there how can we determine the optimum moisture content. All those things will be taught to you later. So let us see the question. So the in situ bulk density and the water content in the so boropit. So from somewhere else we are bringing this soil, okay, and the place from where we are getting this soil, uh, place from where we are getting this soil, uh, it's called a boropit. Okay, boropit means some a pit from where you are boring the soil. So it's a term called boropit. So the boropit, the in situ bulk density uh, of that in that boropit, the density of that soil in the boropit is 17 kilonewton per meter cube. Okay, and the water content is 8% there in the bore pit. So how much excavation should be carried out in the bore pit for each cubic meter of the embankment? So to fill 1 meter cube of the embankment, so our embankment is to be constructed, and this embankment should have two parameters fulfilled. That is, the dry density. This parameter, the condition should be fulfilled. The condition is that the dry density should be 18 kilonewton per meter cube at an optimum moisture content of 15%. Okay, this is the condition that should be followed while constructing the embankment. Okay, so our question is how much amount of soil that we need to carry from the bore pit to build 1 meter cube, means like 1 meter cube of to fill one for each meter cube of the embankment. Okay, so we need to find this out, so that after that, like, so that we can calculate the number of like trucks we need to bring the soil from there. All of this we need to calculate. Like this is the like general how things are done in the field. So we know how at what density our embankment needs to be constructed. So using those values and the in situ values from where we are going to get the soil, we calculate the amount of soil that needs to be transported, and from there we calculate the cost of transportation, number of trucks of soil that are required, all of these things. And in this question also you can see that our G value is given, the specific gravity is given, and our and it's said that water content, the unit weight of water can be considered as 10. It's 9.81 something, so we can consider it 10 for simplicity. Okay, so now let us see how to solve this problem. So we write down, so here we have this, again I will write down the bore pit this side, it's we call it 1, and here we have the embankment, we call it 2. Okay, for the bore pit our gamma is unit weight is 17 kilonewton per meter cube. Water content is 0.08, it is 8%, and our G value is 2.7. These are all given in your question. Okay, for the embankment we have the dry density. Okay, the dry density is 18 kilonewton per meter cube, at a water content of 0.15. Okay, gamma w we are asked to consider. Okay, now for the embankment we know the dry unit weight and we know the water content. Okay, from these two things we can easily find out the total unit weight. Okay, yes or no? So you know, we know that the dry unit weight is equal to the total unit weight weight by this relation we have used many times now in the previous problems. So we know this relation. From this relation we can find out total unit weight as 18 into 1 plus 0.15 equal to 20.7 kilonewton per meter cube. Okay, so the total unit weight of the soil in the embankment we got it. Okay, that we need to achieve, we got this value. Now for now the total unit weight in the borrow pit you can write as this relation easily. We can write this down. Okay, from there if we put the values, this we know it's 17, it was given to us, this is known to us, this is known to us, this is unknown to us. Okay, into 10. From this we can find out our void ratio. Okay, we solve, this is known, this is known, this is known, this is known, this is unknown, right? The void ratio of the borrow pit is unknown, borrow pit soil is unknown. So you can put all the values, rearrange the terms, and you can find out the void ratio at this value. Okay, similarly for the embankment if we write down the same relation again, so this value is known to us, we just found out in the last step, this 20.7 found out. So this is known to us, G is known to us, water content is known to us. So from this we can easily find out E2 as 0.5. Okay, so we have an E1 and we read the void ratio of the borrow pit and the void ratio of the embankment. Okay, that we need to construct. Both of these we know. Now the same concept that we used previously we are going to use, that is the volume of soil solids is going to remain the same. When the volume of soil solids will always remain the same in the uh, in your borrow pit and your embankment, because from there you're carrying the soil and constructing an embankment, right? So the volume of soil solids will all, for a particular volume of soil, particular total volume, the volume of soil solids will always remain the same. The water might differ, the air voids might differ, these things might differ, but the volume of soil solids will always be the same. Okay, so as the volume of soil solids remains the same, you can write volume of soil solids is equal to volume of borrow pit by this. So these two are always same, these two are same, because the volume of soil solids is going to remain the same in both the cases. From there you are taking the soil to, from one point you are taking the soil to another point. Anything else might change, but the volume of soil solids in a particular volume will always remain the same. Okay, the volume of soil remains the same. From this you can write it like this. If you rearrange, you can write it like this. Now let us see the question. What was asked in our question? How much excavation should be carried out in the borrow pit for each cubic meter of embankment? For that means for for volume of embankment equal to 1 cubic meter, how much volume you should excavate in the borrow pit? Okay, so for volume of embankment equal to 1, how much you should excavate? You know all the values. You just put the values and you will get the volume cubic meter. Okay, so this means that to ex to to construct to construct to construct 1 cubic meter of the embankment, 1.143 cubic meter of soil from the borrow pit should be used. Understood? So to construct 1 cubic meter of the embankment, you need 1.143 cubic meter of the borrow pit soil. So using this, you can easily calculate the total number of volume of soil required, because you will know the length of the embankment above which the road needs to be constructed. So you know the length of the embankment, so you can calculate the total volume. From there you will get the total volume of the soil that needs to be constructed. From there you can calculate the total number of trucks, you know the volume that each truck can carry, so you can calculate the total number of trucks. From there you can calculate the cost. So these are typical like borrow pit problems that we like regularly encounter. Now let us go to the next question. Just let me check once. Yeah. Yeah. So next is our problem number 8. So in problem number 8, it's given that a relative density test was conducted on a sandy soil. Okay, so in a sandy soil, previously I told you that this relative density is valid for sands, right? So it shows how dense the sand the soil is, sandy soil. So it's generally valid for cohesionless soils, that is sandy soils. Okay, it is non-sticky kind of soil, sandy soils. So a relative density test was conducted on a sandy soil, and these are the results that we obtained. Okay, so what are the results? So the Emax, the maximum this one void ratio was found out as 0.95. The minimum void ratio means that at the densest state the void ratio was found out as 0.4, and the relative density was found out as 45%. Also it is given to us that the specific gravity is 2.7. We need to calculate the dry density of the soil, it is gamma d, we need to calculate. This is the first part. The second part is, if a 5-meter thickness of the stratum is densified to a relative density set. So initially the soil was had a relative density of 45%. Right. Now you need to now we are the question is that if a 5-meter thick, so the height of the soil is 5 meter. Okay, 5-meter thick soil stratum is to be densified. It means we do some compaction, we pass some roller or something like that of the soil, we densify it so that the relative density increases to 70%. Okay, so soil was there like this initially. Okay, then you densified it, what will happen? Obviously the sand will be more closely packed, so from here the height will obviously get reduced because you are densifying it. Okay, okay, so we need to find out. So this was initially 5 meters, so we need to find out that after densification to 70% relative density, what is the thickness? Okay, how much is the thickness of the stratum? Okay, this is what we need to find out. So let us see the problem. So what is id? Id is nothing but Emax minus E natural by Emax minus E mean. Correct? We know this, right? So now if we put all the values, okay, all the values, we can calculate the natural this E value, the natural void ratio of the soil. Okay, so we put all the values. From here you can calculate E as 0.70. Okay, so this is the natural void ratio of the soil. Now we need to calculate dry density. So now for dry density we know that mud equal to G gamma W plus 1 plus E. Okay, because see gamma total, what is the total unit? G plus SE by 1 plus E into gamma W, but our S is equal to 0, as S equal to 0 because dry soil, dry. So you will get G gamma W by 1 plus C from there. So you get the gamma D is equal to, we put all the values, say 2.7 into gamma W put, then 1 plus 0.70, you get gamma ds 1.58, this is 1, so 1.588 gram per cc. Okay, so first part you have already calculated. So dry density you found out. This is the dry density of the soil. Now next we need to find out this. So after densification to 70%, how much will be the reduction in thickness? So now let us find out first what will be the value of the void ratio when our relative density is 70%. Okay, so it will be somewhat lesser than this value, obviously. So let us find out that value. So we have 70 is equal to E max minus E. Let us multiply this E2 by E max minus E mean. So if we solve this, 0 into 100, na? Just a second. Just wait, let me write it properly. E max minus E. Yeah, sorry. E max by E minus E by E max minus E mean into 100%. Okay. So from here, if we put all the values, so 0.7 is equal to 0.95 minus E2 by 0.95 minus 0.4. So if we solve this, you will get E2 is equal to 0.565. So previously it was 0.7, now it is 0.565. So obviously it will reduce because the soil has been densified, correct? As the soil has been densified, so it will obviously get reduced. So we got this value. Now we can see, now the height of the soil is given as, thickness of the stratum is given as 5 meters. Okay, so now let us consider that it is a it is a not cube actually, cuboidal, like not it, cube has all sides equal, but it's not all the sides are not equal. So let us consider that it is a, see, parallelepiped having height of 5 meter and these other dimensions are 1 meter. Okay, so what will be the volume? Volume will be 5 into 1 into 1 equal to 5 meter cube. So this is an assumption. The height is fixed, but other two dimensions we can just, the height is fixed. The other two dimensions we are just assuming that is 1 meter each. Okay, so if you get, you will get this as 5 meter cube. Okay, now one second. Now let us determine the volume of solids in the initial soil when the relative density was this when the relative density is when the relative density was this 45%. Let us have relative density 45%. We found out that the void ratio is 0.70. In that case, in this scenario, let us find out what was the volume of solids. If we assume this thing, let us find it out. So we know E is equal to Vs. So this will be V1 minus Es by Vs. So if you put E as 0.70, you will get Vs as 2.94 meter cube. Okay, correct. So volume of solids we have got. Okay, now let us come to this again. So E2 is equal to again volume of voids by volume of solids. Now what is the volume of voids? It's the total volume minus volume of solids by volume of solids. Okay, so V2 minus 2.94 by 2.94, and this we know as 0.565. From here we can find out our V2 value, which is equal to 4.601 meter cube. That means initially it was 5 meter cube, right? Initially our volume was 5 meter cube, but now after the densification our volume is reduced, just come to 4.601. Okay, now you need to find out what is the, how much will the this delta you need to find, change in height. So what will be the volumes, you know? So what will be the change in height? H1 minus H2 is equal to delta H is equal to the difference of the volumes divided by area. So what is the cross section area? Nothing but 1 into 1 is equal to 1 meter square. So 1. So it's 5 minus 4.601 is nothing but 0.399 meter cube. 0.4 meter cube. Sorry, not meter cube, meter. Right? So we found out that after densification from relative density of 45% to 70%, the height of the stratum reduced from 5 meter to 5 minus 0.4 meter, that is 4.6 meter. Okay, after densification, so after densification, initially it was 5, now it became 4.6. So let us see how did we find out. Let us go through the problem again and see how we calculated everything. So first we had the relative density of the initial state. From there we got the void ratio of the initial state, that is the 0.7. From there we calculated the dry density of the soil. The first part of our problem gets over here. Now in the second part it's given that if the 5 meter thickness of soil is there, how much reduction in the thickness of soil will be there if that soil is densified to relative density of 70% from a relative density of 40%. Okay, we need to find this out. So what we do is that again we determine the void ratio similar to the first case. What will be the void ratio in the second case? Again we determine this void ratio. Okay, after this what we do is that we consider that the soil has a unit cross sectional area, correct? So from there we calculate the volume of the soil is 5 meter cube, the initial volume. Now you know the void ratio of the soil. Okay, from the void ratio you can find out the volume of soil solids in this 5 meter cube. So in this 5 meter cube, 2.94 meter cube is occupied by the soil solids. So you found out this. Okay, now in the next part what we did was we calculated the volume in the densified state, means when the relative density was increased to 70%. So we knew the volume of soil solids. Okay, and we knew the void ratio. From there we find out the volume of soil solids is always going to remain the same, right? So from there we found out the volume of this uh, densified state. Okay, now from, as we know the volume and we know the cross section unit the cross sectional area is unit 1. From there we could easily determine the change in height. So from 5 meter it will reduce by 0.4 meter. So the final height of the soil strata after densification will be 4.6 meter. Okay. Okay, so let us look into this problem. So in this problem, it's given to us that uh, as I told you, showed you earlier, the liquid limit test, discussed about the liquid limit test. So a liquid limit test was considered using that Casagrande apparatus, where you you counted the number of blows when that the separated soil will come close, and we noted the number of blows and you found the water content, and you got a table where you have the number of blows and you have the water content. So this was the result obtained from a liquid limit test. Okay, so this is the cup of the Casagrande apparatus. So inside the cup there is soil like this soil. So you you made a groove in the soil. What happens, you kept on giving number of blows. Say for when the so initially the water content was say 59. Okay, when the water content was 59, you required 40 number of blows, so that this a certain length of the soil like closes comes near to each other. Okay, both of them come close to each other. Okay, then again you increase the water content, and then again obviously lesser number of blows will be required because the soil is becoming more flowy. Okay, so see, as the number water content you are increasing, the number of blows required is reducing. So you need to find out the liquid limit. So as per definition, what is the liquid limit? Liquid limit is at 25 blows, what is my water content? Okay, so what we need to do is that we need to plot. You need to plot the number of blows here in log scale and the water content here in percent. Okay, so we will get some graph like this, and from there we can find out the liquid limit, which is nothing but the water content corresponding to 25 blows. Okay, so let us see. So this is the number of blows and water content. So this is just I plotted this one in Excel. So this is the log scale. You can see that these are the log scale, and this is a normal scale. The in the ordinate direction, in the x direction, it's a log scale. So you plotted all the values, and what you will get? You will get a, you will just draw a rough say line. Okay, rough line. So this is nothing but our flow line. Now what we do is that this is 10, right? So this is 20. This 25 will be something here in the middle. So corresponding to 25. Sorry. So corresponding to 25, the water content what we get will give you give our liquid limit. So in this case, the liquid limit will be close to about 70%. Okay, so you can draw this in a graph log semi-log paper and do as a homework, and see that whether it's really coming out to be close to 70% or not. Okay, and one more thing you can do is that you can calculate the flow index. Okay, you calculate the flow index. Flow index is nothing but the slope of this line. Slope. Okay, so if the slope is high, that means more easily the soil is losing its strength, right? So higher the flow index means higher easily the soil will get to a more flowy state. Okay, so this is what it is. So now let us look into this problem. Next problem. So the next problem, here we have a overnight soil sample of 200 cc weighs 360 gram. Okay, 360 gram. The specific gravity is 2.7. It's given to us that the specific gravity is 2.7. We need to determine the void ratio and the shrinkage limit. Okay, so we have a overnight soil sample. Okay, its volume and weight is given. So as the soil is overnight, so directly you can write volume of soil solid says 200 cc and weight of soil solid says 360 gram. So these two data are given to you. Also the specific gravity is 2.7. Okay, we need to determine the void ratio, this E, and the shrinkage limit. Okay, so let us see. Now what is the dry density of the soil? You can calculate, right? So what will be the dry density? Dry density nothing but dried weight by dried volume, nothing but this by this. Okay, okay, sorry, one second, not volume solids. Okay, dried volume, this is actually this won't be the, because air also will be there, right? So it will be not Vs, it is Vd. Okay, so in Vd you have both volume of soil solids and also the volume of air. correct? So it will be Vd. So what is our dry density? It's nothing but the dried weight by the dried volume. So we get this as 360 by 200 is, sorry, 360 by 200 is nothing but 1.8 gram per cc. Okay, now again we know this relation, gamma t is equal to gamma w by 1 plus e. Okay, so if we put our values, this is 1.8 we just calculated, this is 2.7, this is 1 in terms of gram per cc plus 1 plus e. From here we can calculate the void ratio as 2.5. So easily you calculated the void ratio. Okay, the first part of our problem is over. So everything was given to us. The dried density we could calculate from the dried volume and the dried weight. From there we use a relation dried density equal to G gamma W by 1 plus E, and we found out the void ratio is 0.5. Now the next part is find out the shrinkage limit. Now I told you beforehand that when this is the, see, this is the water content, this is the volume. Okay, our graph was something like this, right? Okay, so this was our, this is the liquid limit, this is the plastic limit, this is the shrinkage limit. At shrinkage limits, I told you that, I told you beforehand only that at shrinkage limit the soil is saturated, and as we reduce, keep on reducing the water from the shrinkage limit, our uh, the soil keeps on drying, like it's not anymore completely saturated. Okay, so we need to find out this shrinkage limit ws. Now what I told you, I told you that at shrinkage limit the soil is always saturated. Okay, so at shrinkage limit, at shrinkage limit saturation is 1, degree of saturation is 1. Okay, as it is 100% saturated. Now we have this relation as C equal to Wg. Okay, from there if we put the data, W is equal to AC by G to 1 into 0.5, you just calculated in the last step, G is 0.5 and G if you put 2.7 we will get 0.185. Okay, now what is this water content? This water content is nothing but your shrinkage limit. Okay, so you just got your shrinkage limit using the simple fact, the simple concept that at shrinkage limit our soil is saturated. Okay, using this you found out. Okay, now one more thing you might ask, why did we put E is equal to 0.5? This is a valid question, right? Why is E 0.5? From how did we know that E is 0.5 in this case? At this point, how is E 0.5? The fact is that, see here, for an oven dried sample, we determined E. E means when the soil water content is 0, means at this point. At this point, it is oven dried sample. At this point, we did the calculation. At this point, we find out E is equal to 0.5. We found this out. Now, if you look into this graph carefully, we will see that the volume remains constant from this dry state to this saturated state. At shrinkage limit point to the completely dry stage, the volume remains constant. So if the volume remains constant, that means the if the void ratio at this dry state is 0.5, then the at shrinkage limit also it will be 0.5, isn't it? Because the volume is constant. See, here volume is like this. Here the volume keeps on changing, but like as we keep on reducing from the shrinkage limit, the volume is not changing anymore. Volume is constant, right? So we are putting this same E value here to get a shrinkage limit. Understood? So if you know the void ratio of your soil sample at completely dry state, you can calculate the shrinkage limit of the soil. Okay. So let me just see the time. What's the time? Okay, it's already 8. So I will stop here. So I guess this much is enough. So actually I had one more problem. So you may try this problem. Okay, if you face any difficulties, you can like ask me anytime. Okay, let me show you the question. Yeah, so this was the question. The mass specific gravity of a fully saturated specimen of clay having a water content of 40% is 1.88. So you have a fully saturated specimen whose water content is given and the specific gravity is given. Okay, so also on it is given that on oven drying the mass specific gravity reduces. Obviously, when you dry the sample, the water is going out, so the specific gravity of the overall whole mass will reduce. So the specific gravity drops from 1.88 to 1.74. So using these data, we can calculate the specific gravity. We need to calculate the specific gravity of clay and its shrinkage limit. Okay. So if you want, then I can solve this, or else you can try this by yourself. Okay, it's a very not very difficult problem. If you want, okay, I can solve it now. Just will take 5 minutes. Okay. So here the mass specific gravity is given initially, which is 1.88. Okay, and the water content is 40%. Correct. So we can write this mass specific gravity as this is nothing but gamma total by gamma of water. So as it is completely saturated, you can replace gamma total by gamma saturated unit weight. But this, we know this. So from here we can write the saturated unit weight as. Also we know that the saturated unit weight also is not the same. Also the saturated unit weight is this given by this relation. Correct. So you have this and this. So let us substitute this into this. Okay. So from here we get Gm is equal to G plus E by 1 plus E into gamma W by gamma W is nothing but G plus E by 1 plus E. Okay. Now it's given to us that this is 1.88. So you just substitute 1.88 is equal to G plus E by 1 plus E. Okay, so we got this. Now again at saturation, S is equal to 1. Okay, and your water content is 40%. This is also given to us, right? Water content is given. Now if we use our old relation which you have used about 100 times here today, let us use it. S equal to Wg, this relation again. If we put E is, you can write E is equal to Wg by S. So S is 1, S is 1, W is 0.4, so E will be nothing but 0.4 G. Okay, you got this. Okay, now what we will do is that we will substitute this E value in this equation. So from E we will take this and substitute into this equation. Okay, let us see what we get. If we substitute E is equal to 0.4 G in the top equation, we will get G plus 0.4 G by 1 plus 0.4 G equal to 1.88. Okay, and G is equal to, so from there you can get G is equal to 2.9. Done. Now again the mass specific gravity is nothing but T by W. Okay, for dry, now this is the mass specific gravity, and for dry soil this will be replaced by dry unit weight by W. Correct. So from here we can write this by this is given as 1.74. This 1.74 is given value for oven dried sample, right? 1.74 is given. So this you can write. Now there is one relation between this, between G and your shrinkage limit. This you may remember, this is 1 by gamma W by gamma T minus by 100, where this is your shrinkage limit. Okay, so from here G, you already know G. Okay, You know G, that you calculated is 2.9. You put 2.9 is equal to 1 by this, also you know from here. Okay, 1 by 1.74 minus ws by 100. Okay, if you solve this, you can find out your shrinkage limit as 23.10%. Done. So what we did was, we formulated two equations in terms of G. Okay, one from the mass, this mass specific gravity, and one from our void ratio. We formulated these two equations, we substituted one to another to determine the specific gravity. Okay, from there, uh, this was our first part. And then our second part, in our question it was mentioned about the dried soil. It was given that 1.74 is the specific gravity. Using this, we got this relation, and now using these two thing in this relation between G and your shrinkage limit, we could easily find the shrinkage limit. So you may remember this relation for fast calculation, which is essential like for competitive exams like GATE. So you can remember this relation between G and specific gravity, and specific gravity, G and shrinkage limit. Okay, so we calculated the shrinkage limit as 23.10.